Key ideas in quantitative finance, stochastic differential equations. We start with continuous time, that is functions which are continuous, and we're going to then move into discrete time. We start with the description of the underlying. In this case, the underlying is the price of a stock, and this pricing was done, this modeling was done by Louis Bachelier in the 1900 publication that he did whilst in Paris, called The Theory of Speculation. This was very, very important because Bachelier, when he proposed this idea, was the first mathematician to suggest that we could use Brownian motion to evaluate stock options, which is something that we keep doing now and is a critical part of the Black-Scholes formula and many other pricing methods for derivatives. Not only that, in his paper that he published as the result of his doctoral studies, he was the first to use advanced mathematics to model the behavior of the stock market. It was revolutionary at the time because they were regarded as separate worlds. They were regarded as the world of money, completely different and far, far away from the world of mathematics and numbers and exact values for formulas. But Bachelier showed that there is a link, and this contribution is one of the main pillars of modern quantitative finance. This idea was in fact very important because it allows us to use this type of models, stochastic differential equations, to describe what happened with the underlying. Here we have geometric Brownian motion, which is described as the change in the value of the stock, ds, being equal to two terms. A term that is related to a tendency or drift, and a second term that is related to a volatility or a random aspect, a random part of the process. Of course, this is only one of the possible ways in which we can describe the behavior of an underlying, a stock in this case, but there are many other ways that we can use to describe what underlyings do. Because let us remember that when we want to price derivatives, the crucial question is not the price of the derivative itself, of the contract, of the structure, but of what is inside. What is the underlying doing? And to know what the underlying is doing, we can describe that using this type of formulas here. And this is what investment banking and trading and hedging and the whole of the financial markets today do. They try to describe what happens with the underlyings and then look at the consequences of that. The geometric Brownian motion can be slightly rewritten in this way. If we pass to the left-hand side of the equation the S value, the price of the stock, which is very convenient because it allows to see the relative percent change in the stock price, which is what we call the return, to be a function of two things. The first term is a deterministic term and is controlled by a parameter called mu. The second term is a stochastic term, and this is controlled by the vol, the volatility, and this is denoted by the Greek letter sigma. Indeed, what we are saying with geometric Brownian motion is that the return of a stock, that is the relative change in price of a stock between one time and the next, depends on two things. One, that is deterministic, that is the tendency, and the other, which is stochastic, and this is the volatility term. They might have different weights, and if we have a higher tendency, a tendency to go up, then the mu will be high. If the volatility is small, then the changes in price will be small. If the mu, the drift, is zero, then the price, the returns of the stock will tend to be stable, will tend to be zero, and then the jumps will depend on what is the value of the volatility term of sigma, and so on. So by controlling these two things, we can get a whole family of realistic representations of the behavior of the stocks. But this is the theory. In practice, what happens? So if we look at this in discrete time, so what happens between 1 minute and the next, 1 second and the next, 1 day and the next, what we have is that we can represent this continuous process, this continuous stochastic differential equation, through discretization. So we discretize it, we transform it from infinitesimal time changes to finite time changes. So what happens between one day and the next in terms of the price of the underlying. And if we do this, this can be done through this discretization that we have here, which allows us to construct an algebraic representation of this SDE. This algebraic representation that we see in the bottom of the page can be indeed rearranged such that we have one formula that says that the price of the stock at time t plus 1 equals the price of the stock at time t multiplied by all these things that we see in the parentheses. And those things are 1 plus mu, the drift, which is a number, could be 5% or so, times delta t, which if we are talking in terms of days, it could be 1 divided by 250 business days in a year, plus sigma, which is the volatility, and this could be as well a value of, say, 20%, epsilon, which is a draw from a standard normal distribution, and the square root of time, which we have the same delta t as before. So with this formula, we're saying if you know the price of the stock today, and you know these parameters, mu, sigma, and the delta t, the amount of time, you can compute the value tomorrow by making draws from a standard normal distribution. And by doing this, you can jump from one to the next, to the next, to the next days, and obtain simulated values. Here we have 4 graphs showing what will happen with these simulated values in discrete time by having different combinations of the mu and the sigma, of the value of the drift and the volatility term. So we can simulate using Monte Carlo simulation what happens in these situations and obtain representations of what is the realistic stock price that we see, not only in equities, but in other asset classes such as currencies through the Garman-Colhagen SDE and through interest rates, for example, here in a simple Basicek model.